So today we'll be presenting my master's thesis, Deciphering Biotic Responses to Rapid Climate Change at the Pliocene-Pleistocene Boundary. This project took place over the last 2 years under the guidance of my advisor, Dr. Nicole Benuso. The outline for my presentation is as follows. First, I'm going to start off with a very brief introduction and background to the Pliocene-Pleistocene transition, followed by the purpose of our research study, our expected hypotheses, then the methods we use to complete our studies, followed by our results, and I will finish my presentation today with a brief discussion and conclusion. So there are a number of reasons that the research I'm presenting today is important. Currently, the Earth is undergoing major climatic changes as a result of many numerous anthropogenic factors. In addition, the planet is facing its 6th mass extinction event. Taken together, these factors will undoubtedly change the faunal and environmental landscape of the planet. To better prepare for these changes, it's necessary for us as researchers to study times in Earth's history where similar climates persisted. One of those such times is the Pliocene transition. So one of the really main objectives of our study was to study the Pliocene transition in hopes of developing new proxies detailing how modern marine organisms and environments may respond to future anthropogenic climate change. While the Pliocene is a really great time to study climate change, it's very, very difficult. And the reasons it's difficult I'll talk about in a little bit, but this study is really important because, as Nicole kind of touched upon, this is the first paleoecological study of the Pliocene transition in the Eastern Pacific. So all the results that I gathered today have never really been done before. For that fact, really, my study is really going to be the basis for a number of other studies which hopefully will be completed not only in Southern California but across the Eastern Pacific region. Once again, I am studying the Pliocene transition. The Pliocene spans a time period from approximately 5.3 to 2.58 million years ago. The Pliocene time is a really unique time in Earth's history because it's the only time in recent history where temperatures have been warmer than modern. In addition, we start to see the emergence of a number of modern fauna during the Pliocene interval. Taken together, this makes the Pliocene a really unique laboratory for studying climate change. Although the Pliocene is regarded as a relatively warm period in Earth's history, by about 3 million years ago, we start to see ice sheets develop in northern latitudes. This cooling trend continues into the Pleistocene, which stretches a period of time from 2.58 to about 11,700 years ago. The Pliocene is our most recent glacial period and is dominated by about 30 glacial and interglacial cycles. There are a number of reasons behind this major climate change at the Pliocene transition. Some large-scale changes, as in Milankovitch cycles, could have impacted climate, but for the focus of this study, we're actually going to focus more on smaller tectonic changes. And the major tectonic change going on during the Pliocene transition is the closing of the Panama Isthmus. So beginning around 3.5 million years ago, we start to see this emergence of this land bridge known today as the Panama Isthmus. The emergence of the Panama Isthmus is a direct result of a collision of 3 plates. So we have the South American plate moving to the northwest, and then the Caribbean and Nazca plate moving to the east. Once these plates collided, we uplifted this bridge of land known as the Panama Isthmus. So the uplift of the Panama Isthmus was significant for a number of reasons. Most importantly, it changed ocean circulation patterns. Prior to the Panama Isthmus closure, we really had one circulation pattern that circulated waters between the Atlantic and the Pacific. After the closure of the Panama Isthmus, we start to see the emergence of modern ocean circulation patterns. That is, we have distinctive ocean circulation patterns in the Western Atlantic and in the Eastern Pacific. Ocean circulation patterns distribute sea surface temperature and nutrient availability across the globe. When we change ocean circulation patterns, we change the way that we distribute these variables. When we change the way we distribute these variables, we're often going to lead to stress on our marine communities. And there are a number of results that could happen as a consequence of this stress. And 2 of those results are mass extinction and turnover. So as a result of this stress after the Panama Isthmus closure, we in fact do see a gradual mass extinction event at the Pliocene-Pleistocene boundary. During this mass extinction event, a number of marine organisms go extinct, including planktonic forams, some bryozoa, echinoids, bivalves, ostracods, and brachiopods. In addition, a number of marine mammals also go extinct at the Pliocene boundary. The Pliocene boundary is a really unique time to look at an extinction event because turnover rates were relatively rapid during this period. Turnover refers to the filling in of new species as older species become extinct. Turnover was so rapid at the Pliocene transition in well-studied regions like the Western Atlantic, we actually find that diversity either remains constant or increases during this interval, which is almost opposite of what we would think when we had an extinction event, where we would expect to see diversity decrease as organisms are dying off. So one of the main focuses of our study today is to really compare our Eastern Pacific results with previous studies from the Western Atlantic region. The Western Atlantic region is probably the most studied Pliocene region across the globe. And from those previous studies, we're able to get a number of oceanic and paleoecological trends. The first is that during the Pliocene transition in the Western Atlantic, we see a decrease in sea surface temperature along with a decrease in nutrient availability and upwelling. In addition, sea surface temperature seasonality increases into the Pleistocene. Sea surface temperature seasonality refers to the differences in temperatures between winter and summer. In the Western Atlantic region, 70% of mollusk species go extinct during this interval. However, due to our rapid turnover rates, we either see diversity remain constant or increase. For those organisms that did survive the Pliocene extinction event, many of those saw a change in morphology. That is, they saw a reduction in their body size. This reduction is most likely related to the decrease in sea surface temperature and the decrease in availability of nutrients. While this study is really the first to take place in the Eastern Pacific, a number of studies have been conducted in the equatorial Pacific region. And from those studies, we can start to get a few general trends about what's going on in the ocean during this time. The first is that sea surface temperature decreases into the Pleistocene. In addition, in the equatorial Pacific, we also see an increase in nutrient availability and upwelling, or it remains constant. So as I mentioned, there's really not too many Pliocene studies from the Eastern Pacific region. And that's because it's extremely difficult to locate the boundary. One of the reasons it's difficult to locate the Pliocene boundary is that there is a large regression occurring at the Pliocene transition. This regression makes it difficult to find a preserved section of marine Pliocene boundary materials. As our regression moves in, we often see shallower waters, and our Pleistocene formations become more terrestrial. In addition, Pliocene sediment is extremely young sediment. So especially in California, a lot of development has occurred that has either removed the Pliocene sediment or built over it, making it virtually impossible for us to find sections. However, we were lucky enough to find a preserved section of the Pliocene boundary. And there are a number of ways for us to confirm that it is indeed the Pliocene boundary. For the purpose of our study today, we're going to be using a planktonic foraminifera biostratigraphic analysis. So basically, we're looking at foram that swim in our sediment. A number of zonal schemes have been already completed that dictate where the Pliocene boundary is using these planktonic foraminifera. 3 schemes that I looked at very closely included Banner and Blow, Boley, and Engel. After preliminary work at our study site, it occurred to us that it was most advantageous to use Engel's 1967 study. His study recognizes the Pliocene boundary at a change in coiling direction between a particular foram. And this foram is Globeritalia pachyderma. So Globeritalia pachyderma actually changes coiling direction when it's in cold and warm water. So in warm water, like we would expect to see in the Pliocene, Globeritalia pachyderma coils clockwise or dextrally. As you move into colder waters, which we would expect to see in the Pleistocene, Globigeritalia pachyderma coils counterclockwise or sinistrally. So when we went to confirm our boundaries, we were really looking for the transition in coiling directions between Globigeritalia pachyderma. So our study site is in Southern California, in San Diego County at Tourmaline Surf Park. Tourmaline Surf Park is northwest of San Diego and north of Pacific Beach. We're looking at the San Diego Formation at Tourmaline Surf Park. Picture A shows our northmost section of project area, and B represents the southmost section of our project area. Our project area stretched approximately across 150 meters of beach. As you can start to see from these pictures, the San Diego Formation is a mainly sandstone unit. However, it does have a couple unique trends. One, the San Diego Formation was deposited in a shelfal environment. That helps us recognize that we have a number of fossil horizons that have been preserved in the sediment. In addition, we can start to see in B that we have this large conglomerate layer represented near the top of our section. This conglomerate layer is believed to represent the inferred Pliocene-Pleistocene boundary in the San Diego Formation. However, no work has really been published confirming that that is indeed the Pliocene-Pleistocene boundary. It's also important to note that when we look at this figure, if this large conglomerate layer does indeed represent the Pliocene-Pleistocene boundary, at our study site, we're really not going to be able to work with much Pleistocene material. And we can start to see that in B again. So our study today really has four objectives. And the first is to locate the Pliocene-Pleistocene boundary using the coiling direction of Globigeritalia pachyderma. Next, we're going to explore marine invertebrate responses to Pliocene climate change in the Eastern Pacific through looking at changes in community composition and diversity. Thirdly, we're going to document changes in sea surface temperature seasonality, and nutrient availability. And finally, we're going to use statistics to determine relationships between organisms and changes in sea surface temperature and nutrient availability. So we have four really distinctive hypotheses for this project. And the first is that we do in fact believe that the Pliocene boundary is located approximately 25 meters up our section at the site of the large conglomerate layer. In addition, we expect to see a decrease into diversity into the Pliocene as community composition changes sporadically throughout the section. We believe that sea surface temperatures will decrease as sea surface temperature seasonality increases. In addition, we also expect to see an increase in nutrient availability. Finally, we do believe that there will be a statistical difference between our Pliocene and Pleistocene horizons. So our study is really broken down into three main components: a taxonomic analysis, an environmental analysis, and a statistical analysis. So the first thing we had to do to begin our taxonomic analysis was describe the fossil beds. And we went to Tourmaline Surf Park and actually described the fossil beds using a method put forth by Kidwell in 1986. Once we identified the fossil beds, we had to sample those fossil beds. We took bulk sediment samples at these fossil beds. So we tried to get about 2 5-gallon buckets worth of sediment from each fossil bed. When we collected those 2 buckets, we tried to get each bucket approximately 2 meters apart. Once we actually had our macroinvertebrates sampled, I spent the summer picking through them and identifying our macrofaunal. To identify the macrofaunal, I used old papers describing organisms from the Pliocene and also a collection of pictures that I was able to take at the San Diego Museum of Natural History. Next, we needed to look at abundance and community composition. Abundance really just refers to the number of specimens that I found in each fossil horizon. Community composition just documents changes in taxa throughout my fossil horizon. When we looked at diversity, diversity is a measure of taxonomic richness of a particular horizon. To determine diversity, we use the Shannon Diversity Index. When we saw an increase in the index, that means we also have an increase in diversity. Finally, we needed to sample for our forams. So we needed our forams to actually locate the Pliocene boundary. So our 4AM samples were taken approximately every 1.5 meters up our section or at known fossil sampling locations. Once I collected the 4AMs, I spent a lot of my summer picking through the 4AMs and identifying the planktonic 4AMs. Next, we have our environmental analysis. Our environmental analysis is split into two parts: a stable isotope analysis and a nutrient analysis. Our stable isotope analysis was completed by the Saskatchewan Isotope Laboratory at the University of Saskatchewan. So we sent a number of gastropod and bivalve samples for analysis. We were not only looking for changes in sea surface temperature, but also changes in sea surface temperature seasonality. So to ensure we had enough data for sea surface temperature seasonality, we had to sample or micromill our gastropod shells at growth lines. So every day, a gastropod adds another growth line. So sampling at these growth lines allows us to record the periodicity that we would need to determine seasonality. When we ran the stable isotope analysis, or rather the University of Saskatchewan ran the stable isotope analysis, we're looking for a change in the del O18 ratio, so oxygen 18 over oxygen 16. Based on our calcium carbonate material, we would indicate colder temperatures by an increase in the del O18 ratio and warmer temperatures by a decrease in the del O18 ratio. Next, we needed to perform a nutrient analysis, and to do that we used an ICP-OES. The first thing I had to do was actually find an acceptable measure to really measure nutrients in a mollusk shell. So after reading a number of research studies, I concluded that for our study, using the barium-calcium ratio would be the most advantageous. The barium cycle in the open ocean is illustrated in this diagram. There are a few general trends about barium. The first is that barium is usually depleted in surface waters, and it is enriched in nutrient-deep water. In addition, we see increases in barium with increased phytoplankton blooms, increase in upwelling, and increase in river input. Taken with all those factors, it's concluded that barium is a good indicator of nutrient availability. So next we had to run an ICP-OES, which I did with the help of Dr. Woods in his lab at Cal State Fullerton. So I selected 2 argopectin samples from each sampling horizon. Those shells then had to be crushed and powdered, dissolved, microwave digested, and eventually run through an ICP-OES. ICP-OES uses elemental wavelengths to determine elemental concentrations within our data. Finally, the last part of our project is completing a statistical analysis. As I mentioned before, when we looked at the inferred location of the Pliocene-Pleistocene boundary, so that large conglomerate layer, we didn't really have much Pleistocene material above it. For that reason, we really wanted to broaden the spectrum of our statistical analysis to be able to really prove that there is a statistical difference between Pliocene and Pleistocene horizons. So in order to do this, we had to collect information from a number of other sources. So the first thing we did was look at the Linda Vista Formation, which is the Pleistocene formation that sits stratigraphically above the San Diego Formation in San Diego County. So again, the Museum of Natural History kindly donated all of their community and organism records from the Linda Vista Formation. So all of those records were collected around San Diego County, and we combined them into one data set. Next, we wanted to have a comparison closer to Orange County. So we used a 2000 study by Powell and Stevens that documented organism changes in the San Pedro Formation. Again, the San Pedro Formation is a Pleistocene formation that's found in Orange and LA counties. Powell and Stevens' study took place in the Coyote Hills, so in Fullerton and Buena Park in Orange County. Finally, we used another San Pedro Formation study by DeLong, which documented organism changes in the Pleistocene from Signal Hill, California, which is located in LA County. After we had all of our fossil horizons, so all of our Pleistocene data combined with our data from Tourmaline Surf Park, we ran 3 statistical tests: clustering analysis, NMDS, and an analysis of similarity. So as we move into the results section, the first thing we really need to do is talk about our stratigraphic section and our fossil beds. So as you can start to see from our strat column, the San Diego Formation had a pretty much uniform composition throughout the entire study area. The San Diego Formation is a relatively fine to medium light tan sandstone, and that really doesn't change much throughout the section. Of course, to us, the most important were those 9 fossil beds that we located in the San Diego Formation. So our lowest fossil bed A, is located about 1 meter above the base of our section. Our 9th fossil bed, so our final fossil bed in this study, would be shell bed I, which is located right below that large conglomerate layer. Again, that large conglomerate layer is thought to be the Pliocene-Pleistocene boundary, so potentially for us, when we started looking at our study, shell bed I could represent Pleistocene material. So when we looked at abundance throughout the section, abundance varies basically based on sampling methods and error. So we kind of discarded those results right now, and it varied sporadically through the section. Again, what's more important to look at when we're discussing taxonomic characteristics is changes in community composition. So at Tourmaline Surf Park, we found a total of 36 different taxa, and that was through the collection of about 1,000 samples. When we look closer at our community composition, we notice that essentially fossil horizons A through H are dominated by similar organisms. Those organisms are argopectins, pectin helii, and the gastropod Opalia vericostata. As we move into our latest fossil bed, so that fossil bed right below the large conglomerate layer, we start to see a shift in dominance between our taxa. So at fossil bed I, our most dominant taxa are Pinope ampla, Olivella biplicata, and Leucinoma annulata. So this shift in dominance between A through H and I tells us that, well, there is a likely turnover event occurring somewhere in this horizon, and that something is changing between these horizons to precipitate this turnover event. So the next taxonomic analysis we need to look at is diversity. As we can see with our diversity line plotted against our strat column, diversity changes pretty sporadically throughout the section, with an increase as we move into, decrease as we move into fossil bed I. When we take a larger look at our diversity graph, we notice we have a peak at horizon H and dips at E and G, meaning those are our points of our least diverse fossil beds. If we added the location of that inferred Pleistocene boundary, we see a decreasing trend as we move into the Pleistocene. Now that we've looked at our community composition and diversity, it allows us to speculate on the location of our turnover events in the San Diego Formation. So at fossil horizon I, 11 new species were introduced that were not previously observed in our older fossil beds. Some of those species include the gastropods Crepidula adunca, Olivella biplicata, and Yatone festiva. In addition, a number of new bivalves are introduced, including Donax goldii. At fossil horizon I, there are only 3 overlapping species with the rest of our fossil horizon, so A through H. Those 3 species are argopectin, pectin helii, and Leucinoma annulata. So the first thing that I really thought when I saw 11 new species at I is that, wow, we have evidence for an extinction event at these fossil horizons. So we've really actually located the extinction event in the San Diego Formation. However, when I researched how many of our A through H fauna actually went extinct at the boundary, there were only 3. 2 of those were Tugali and Swiftopecten parmeli. Because we only have 3 organisms going extinct but 11 new species introduced. This kind of shifts our focus from an extinction event occurring at that horizon to rather distinctive environmental changes causing this turnover in species. So one of the reasons that we might have environmental changes at fossil horizon I could be that it is located at, above, or below the Pliocene-Pleistocene boundary, where we know there are known climate changes. So again, to locate the Pliocene-Pleistocene boundary, we used a planktonic foraminifera biostratigraphy. So as I looked through all of our samples, represented by the triangles on our strat column, we found 9 total planktonic species. When we take a closer look, these are our 9 planktonic species that we found in the San Diego Formation horizons. As you recall, we're really looking for that Globeritalia pachyderma. So we're looking for a change in coiling direction between a counterclockwise Globeritalia pachyderma and a sinistrally coiling Globeritalia pachyderma. So what we found when we were looking at our forams was that we do see our dextral coiling Globeritalia pachyderma in lower sampling horizons before that conglomerate layer and below it. It's also important to note that when we look at the foram biostratigraphy, that the solid lines indicate the actual presence of these planktonic forams in the sample, and the dotted lines indicate the inferred presence based on information about the foram's known stratigraphic and taxonomic range. Dextrally coiling Globeritalia pachyderma in lower horizons, and when we get to our sampling locations at and right below that large conglomerate layer, we see our sinistrally coiling Globeritalia pachyderma. So at least preliminarily, that suggests that yes, indeed the Pliocene boundary is located below that large conglomerate layer. So there are a number of other factors that support our decision to place the Pliocene boundary at that location. And the first is that regression I talked about. So at the Pliocene boundary, we have a large regression. At our study site, we have a large channelization event that occurs at the Pliocene boundary, which likely resulted from regression. In addition, underneath the Pliocene boundary, at fossil bed I, we see a lot of reworked sediment material and fossil hash. So this at least indicates to me that something chaotic is going on at this point in geologic history, also confirming the location of the Pliocene boundary. Finally, a paper by Johnson suggested that these 3 gastropods, so Crepidula adunca, Olivella biplicata, and Yatone festiva, are purely Pleistocene gastropods. These gastropods only occur at fossil horizon I. So again, it's the really last piece of the puzzle that confirms to us that yes, indeed, the Pliocene boundary is located right below that large conglomerate layer. So next we need to move into our environmental analysis results. The first environmental analysis that we completed was a stable isotope analysis to determine sea surface temperature. We tested 3 gastropods, 1 from the Pliocene, represented by the green line, and 2 from the Pleistocene. The first thing you might notice from this graph is that we have gaps in some of the lines. These gaps likely represent shell impurities where samples could not have been taken. However, we can extrapolate sea surface temperatures from existing points. The first trend that I really see when looking at sea surface temperature seasonality, just sea surface temperature, is that we don't really see any major peaks and dips. So all the temperatures really vary within themselves. So there's really not times that we can pinpoint colder and warmer temperatures as we look at Pliocene and Pleistocene material. When we analyze our sea surface temperature samples more in depth, we're able to pick out seasonality. So starting with our Pliocene sample, which was taken from A, so again about 1 meter above the base of our section, peaks in the data represent summer temperatures, represented in orange. Dips in the sea surface temperature data represent winter temperatures, represented in blue. So what we found when I combined the summer and winter temperature was that Pliocene sample A116 has a summer average of 14.3 degrees Celsius and a winter average of 11.8 degrees Celsius. The seasonal difference between these two is about 2.5 degrees Celsius. When we look at our first Pleistocene sample collected from that fossil horizon I, which we believe is right at the Pliocene-Pleistocene boundary, we have a summer average of 13.6 degrees Celsius, a winter average of 11.7 degrees Celsius, and a difference of about 2 degrees at 1.9 degrees Celsius. Our final Pleistocene sample, also collected from fossil horizon I, right below the conglomerate layer, had a summer average of 14.3 degrees Celsius, a winter average of 12.1 degrees Celsius, and a difference again of about 2 degrees Celsius at 2.2 degrees. So the second component of our environmental analysis was to look at a nutrient analysis throughout the Pliocene. The first trend you really can see from our green nutrient analysis line is that we don't have any data for fossil horizon I. We were unable to sample from fossil horizon I due to its location under a large overhanging conglomerate layer. So taking bulk sediment from there seemed a little dangerous. So any results that we collected from sampling horizon I were done in the field. However, when we look more closely at our average nutrient availability graph, we can see that we only have one really decrease in nutrient availability, which was low in our strat section at fossil horizon B, and we have a relatively steady increase throughout the rest of our section. Our high R-squared value of 0.87 indicates that there is a significant relationship between nutrient analysis and time, represented by the fossil horizons. If we add the location of our Pleistocene boundary now, we can extrapolate our results to say that most likely nutrient availability did increase into the Pleistocene region. One of the really cool trends that I came across when going through all my data was when I superimposed my nutrient availability graph with our with our diversity graph. What I found was that a number of peaks and dips within both our nutrient availability data and our diversity data seem to align. Or maybe not align, but rather nutrient availability might precede the movement of diversity. This could really just be a big coincidence, but at least when I was going through my results, this told me that there might be some bigger relationship between nutrient availability and diversity. Finally, the last part of our project was to look at a statistical analysis of our horizons. Before I begin with the statistical analysis, I just want to review the sampling horizons that were used. So again, A through H in any of our statistical analysis represent our San Diego Formation horizons. SP represents our San Pedro Formation horizons that were collected in the Coyote Hills, so Fullerton and Buena Park in Orange County. Powell and Stevens, who completed the work on the San Pedro Formation in the Coyote Hills, split SP into a number of different units. Those refer to SPR, SP Plio, SPM, and SPU. So you will see those on our statistical analysis today. SH represents San Pedro Formation from Signal Hill, California, from that DeLong study. And finally, LV represents the Linda Vista Formation that was gathered from the data from the Museum of Natural History in San Diego. LV data represents a number of different sampling localities across San Diego County. So the first stat test we used was a clustering analysis. Clustering analysis really helps us determine groups within our data set. But it is really up to the researcher to determine how these groups form. So when we look at clustering analysis, samples that plot on the same tree, this is a dendrogram, so plot essentially on the same graph, are considered more similar. We can read our cluster analysis plot anywhere along the y-axis. If we read it at a similarity of 0, these are going to be our more general groups. As we move down the y-axis to a similarity of 100%, these are going to be our more specific or precise groupings. So when we really take a look at our statistical analyzed fossil horizons, if we look at really general groups, I can see three. The first is SPR, so San Pedro Formation from Coyote Hills, followed by all of our Tourmaline Surf Park sampling horizons, A through I, followed by all of our known Pleistocene locations, so LV, SH, and SP Plio. It should be noted that the plotting of SPR away from all the other SPM groups allows us to really reject SPR in our study. We considered it an outlier, and that trend will be confirmed in our NMDS plot. As we go down the y-axis, so getting into more similar groups, there are a few noticeable groups. The first is that I plots independently of all the other San Diego Formation horizons, A through H. In addition, Linda Vista, so LV, plots separately from SH, which plots separately from all the other SP Formation horizons. So again, it's really up to the researcher to determine how these groups basically formed in our clustering analysis plot. And what I basically found is samples that plotted closer together had the most taxa in common. So when we look at this group right here, SPU and SPM, a part of the smaller or the larger SP group, they have 21 taxa in common. As we move farther away from SPM, we have fewer taxa in common. So SP Plio only has 18 in common with SPM, SH only has 12, LV 4, and then all of our other San Diego Formation horizons had 2. Again, SPR had 0 in common with any other group. In addition to taxa commonalities within our data, there's definitely a certain degree of time variation on our clustering analysis plot. Again, all of our Pleistocene samples plot within a larger group, followed by our early Pleistocene, perhaps late Pliocene, San Diego Formation horizon I, and then our late Pliocene A through H San Diego Formation horizons plot together. So in order to really confirm these trends, we had to run another statistical analysis. That statistical analysis is called non-metric multidimensional scaling, or NMDS. Much like clustering analysis, NMDS plots samples that are more similar closer together. When we look at our NMDS plot, we really only have one distinctive group of data, and that really is the samples that essentially plot on top of each other. And for us, that's going to be our San Diego Formation horizons A through H. Again, we do see a lot of similarity based on the proximity that these samples plotted. SP Plio, SPU plotted very closely together, so that tells us that they are probably really highly related. Again, SPR plots really far away from any other samples, which supports our decision to consider SPR an outlier. Now, NMDS plots are also important because the alignment of samples along both the X and Y axis can determine or are determined by certain environmental variables. Again, it's up to the researcher to really determine what environmental variables control the different axes. So again, the first thing I saw when I looked at my NMDS plot was that there is a definite time component going on across the x-axis. So all of our late Pliocene San Diego Formation horizons plot together close to the 0 point on the x-axis, followed by our early Pleistocene, late Pliocene San Diego Formation fossil bed I. Then again, all of our strictly Pleistocene samples plot very closely together. You may recall I said that environmental variables control the x and y axis. Time is not an environmental variable. So what we really had to think about were what variables were changing through time as we moved into the Plio-Pleistocene. And when we studied the x-axis, we determined that the best variable controlling the alignment of these samples is going to be sea surface temperature. So warmer samples plot closer to that 0 point on the x-axis. So again, if the late Pliocene we know was warmer, A through H would be our warmest sample. and then temperatures get cooler as you go down the x-axis. Notice that temperatures get cooler, not necessarily colder. Next, we had to determine what variable controlled the y-axis. And for us, the best choice was really water depth. So our shallow samples should plot closer to the 0 point on the y-axis. So this would say that all of our Pleistocene SP plio formations are, SP formations are shallower than I and A through H. Again, if A through H was deposited in the late Pliocene, we know we have a regression moving into the early Pleistocene. A regression would reduce ocean depth or water depth, so it makes sense that we would see a reduction as we go down the y-axis. So then we actually had to prove that our horizons were different. And to do this, we ran an analysis of similarity, or an ANOSIM. ANOSIM tests our null and alternative hypotheses. Our null hypothesis was that there was no statistical difference between Pliocene and Pleistocene horizons. Our alternative hypothesis was that there was a statistical difference between Pliocene and Pleistocene horizons. When we ran an ANOSIM test, our results computed a global R value of 1. This extremely high R value allows us to reject the null hypothesis and accept the alternative hypothesis that our Pliocene and Pleistocene horizons are statistically different. In addition, ANOSIM also runs a pairwise test, which tests groups of data with each other to determine similarities and differences. As you recall from our NMDS plot, the only real group of data we had was A through H, which essentially plotted on top of each other. So our pairwise test actually tested A through H with every other sampling horizon that we statistically analyzed. And again, what we found is that when A through H was compared with every other fossil horizon, we got the same R value of 1, meaning we reject the null, and accept the alternative hypothesis that, yes, there is a statistical difference between Pliocene and Pleistocene horizons. So as we really thought about discussions and conclusions for my paper, the basic idea we had to really prove was how these factors could change into the Plio-Pleistocene. So when we first look at a taxonomic analysis, we know community composition changed throughout the section with that turnover event occurring at fossil horizon I. In addition, we also saw a decrease in diversity as we entered fossil horizon I, so the inferred Plio-Pleistocene boundary. So there are a number of factors which could have led to this result. The first was that we saw a sea surface temperature decline into the Pleistocene. Sea surface temperature is probably the most important variable which dictates what particular organisms can live in a particular area. Organisms are very sensitive to sea surface temperature change. So if the sea surface temperature decreased, organisms either had to adapt very quickly or migrate out of the area into a new community. If they could not adapt, again, they would eventually go extinct, at least at that area. In addition to a decrease in sea surface temperature, we also saw nutrient availability changes. Nutrient availability essentially dictates basically how much or how many organisms a particular community can support. So changes in nutrient availability would essentially change how many organisms that environment could support. So a decrease in nutrients might mean a decrease in organisms, where an increase might mean an increase in organisms. In addition, we have that major regression I've been talking about. So into the Plio-Pleistocene, we saw a reduction of the shelf environment by about 25%. As you may recall, the San Diego Formation is a shelf formation, so it makes sense that we would see a shallowing throughout our section, which we believe controlled the y-axis on our NMDS plot. We have evidence for this regression at our study site. We have that large channelization event at the Plio-Pleistocene boundary, which likely was a result of the regression taking place. In addition, we really wanted to look at shallow and deep organism depth to really determine that organisms might have changed as a result of regression. So I spent a lot of time looking at all the taxa from my study and determining if they were shallow or deep water taxa. So shallow taxa were regarded as any taxa that could live in less than 130 meters of water, which is the modern cutoff for the shelf. Deep taxa could live in a wider ranges of environment. So what I found was that in fossil horizon I, two particular taxa, the bivalve Donax goldie and the gastropod Crepidula adunca, are extremely shallow water organisms. That is, they can only live in about 5 meters of water or less. When I looked at the other organisms found in A through H, many of those organisms had a much wider range of water depth that they could live in. So therefore, the presence of these organisms really supports that we do see a shallowing, at least in the San Diego Formation at Tourmaline Surf Park, during this transition. Again, this shallowing trend really supports our guess that water depth controls the y-axis on our NMDS plot. In addition to sea surface temperature, nutrient availability, regression, we also have to think about tectonic activity. During the Pliocene, the San Andreas Fault was active during this time, in addition to a number of other faults in the San Diego Basin, which is where the San Diego Formation was deposited. These faults would act to disrupt or destroy environmental patterns, causing stress possibly on these marine invertebrate communities. Next, we need to think about our stable isotope analysis. So just a review of the basic trends we saw from our results. There's little variation between Plio and Pleistocene temperatures, as shown by the lack of extremes on our graph. We had a seasonality range of about 1.9 to 2.5 degrees Celsius. That's a very small change in seasonal temperatures from the Plio to the Pleistocene. However, when we looked at modern sea surface temperatures, we concluded that our results mostly fell within modern sea surface temperature range, which is about 12 to 17 degrees Celsius. Why these results may seem generally pretty vague, but it's important to remember that this is the first time sea surface temperature seasonality has ever been looked at in the Eastern Pacific. And our rather distinct trends in our variable could be a result to the method of cooling, or really the timing of cooling. Although the Pliocene was warmer and the Pleistocene was colder, when you hit that boundary, we didn't just flip a switch and things got colder. It was more often a gradual cooling of sea surface temperature. Finally, we looked at nutrient availability, with our most basic trend being that we see an increase in nutrients throughout the late Pliocene, which we extrapolated to include the early Pleistocene. There are a number of reasons for this increase in nutrients. The first is, again, sea surface temperature. Colder water is traditionally much more nutrient dense. In addition, we see an increase in upwelling during the Plio-Pleistocene transition. This upwelling is driven not only by temperature differences, but also by the intensification and establishment of modern wind patterns, as wind pattern essentially drives upwelling. Next, we had a thermocline shoaling event at the Plio-Pleistocene transition. The thermocline refers to a layer in the ocean in which water temperature changes more rapidly than depth. Shoaling is really just another word for shallowing. So when we had our shallow thermocline as we moved into the Pleistocene, when you upwell water, as shown in this first picture, you're upwelling water from deep, nutrient-rich water. When we have a deeper thermocline, as was observed in the Pliocene, when you're upwelling water, you're really upwelling from this thermocline layer, which might not be as nutrient dense. In addition, we could have saw a localized increase in nutrients, and that is through river input. When we think back to our barium cycle, we know barium peaked with increased river input in an area. At the Plio-Pleistocene boundary, we have this large conglomerate layer, which is really indicative of our channelization event or river input into our system during this time. Again, one of the major conclusions we wanted to draw from this study was determining how our trends related to trends discovered in the Western Atlantic. So we looked at really three basic trends: diversity, sea surface temperature seasonality, and nutrient availability. So when we look at our diversity data from the Eastern Pacific, we saw a decrease in diversity into fossil horizon I, or the early Pleistocene. In the Western Atlantic, we either saw that constant diversity or a slight increase in diversity as turnover rates were very rapid. Next, when we look at sea surface temperature seasonality, we had a near constant seasonality rate in the Pliocene in the Eastern Pacific compared to an increase in seasonality in the Western Atlantic. Our nutrient analysis from the Eastern Pacific showed a nutrient increase through the late Pliocene, which we extrapolated to include the early Pleistocene, with that increase in upwelling. In the Western Atlantic, we saw a decrease in nutrient availability as upwelling also decreased. So there are a number of reasons that our trends may be different from the Western Atlantic. The first is just volume of studies. As I mentioned, the Western Atlantic is probably the most studied Pliocene region across the globe. Because they have a larger volume of study, they can draw more concise results than just our preliminary study from the Eastern Pacific. In addition, there's different ocean circulation patterns affecting the Western Atlantic and the Eastern Pacific during this interval. Different sea surface or ocean circulation patterns redistributed sea surface temperature and nutrients differently in both oceans. And finally, we have to think about tectonics. The western coast of the United States during this region and today is much more tectonically active than the east coast of the United States or the Western Atlantic region. Tectonics not only deform environment, but could disrupt our marine invertebrate communities. Again, this study is really a baseline study for future research into the Pliocene boundaries. So if this study were to continue, or if another study were to come into being, I had a number of suggestions as how my study could be improved. And the first is we would need to locate more preserved sections of the Pliocene boundary, or larger preserved sections essentially. At the San Diego Formation, we probably only had maybe 1 meter to 5 meters of Pleistocene material, which we actually couldn't pull any fossils from. So we're going to get the best results from this study when we have large Pliocene material, which is underneath Pleistocene material. However, as I mentioned before, it's extremely difficult to find the Pliocene boundary in California or along the Eastern Pacific during this interval. And I would also have loved to, or in the future would like to age date my samples. There's always some degree of time averaging when we are looking at fossil horizons. So especially on the statistical analysis, it's difficult if we had different degrees of time averaging. So if the San Diego Formation only represented tens of years of time averaging, and our other horizons represented tens of thousands of years of time averaging, it's really difficult to compare those two. So to reduce that variable, you would need to age date your samples. So in summary, I just want to briefly go over our objectives and hypotheses once again. So the first goal of this study was to locate the Pliocene boundary in the San Diego Formation. And we believe that that Pliocene boundary was located approximately 25 meters up the section at the site of the large conglomerate layer. So using the coiling ratios of Globigertalia pachyderma, we concluded that yes, the Pliocene boundary is located somewhere beneath this large conglomerate layer at Tourmaline Surf Park. Secondly, we wanted to test diversity and community composition changes. So we believed that diversity would decrease into the Pleistocene as community composition varied. Again, we did see a decrease in diversity into the Pleistocene, and we saw changes in community composition. The most notable community composition change was between horizons A through H and I. Here's a location of a turnover event, and that turnover event was a result of numerous environmental changes taking place during the Pliocene. Thirdly, we looked at different environmental variables dictating organism changes. So we believe sea surface temperature would decrease as sea surface temperature seasonality increases. In addition, we also thought nutrient availability would increase. So from past studies, we do know that sea surface temperature decreases into the Pleistocene. Sea surface temperature seasonality remained constant, and nutrient availability at least increased throughout the late Pliocene interval. Finally, we wanted to test that our fossil horizons were statistically different. And we hypothesized that indeed we would find a statistical difference between our Plio and Pleistocene horizons. Using 3 statistical tests, clustering analysis, NMDS, and a NOSIM, we concluded that our Pliocene horizons, so San Diego Formation A through H, are statistically different from our Pleistocene horizons, represented by I, SP, SH, and LV. Okay, so this project would not have been possible without a number of people who helped tremendously. The first is Tom Demaray from the Museum of Natural History in San Diego. He not only went into the field with Nicole and I for the first time, but he also allowed me access into their fossil collections, which I was able to photograph, and that aided tremendously in my identification of my taxa. Next, Will Barrelson from USC. He allowed me the use of his very cool desktop SEM to take pictures of my forams. Bill Patterson at the University of Saskatchewan in the Saskatchewan Isotope Laboratory ran all my stable isotope analysis, which we were really lucky we were able to do. And one of the reasons we were able to do that was from a CSUF ASI very generous student research grant. And then finally, just the Department of Geology here at CSUF has been so incredibly supportive and helpful throughout these 2 years, so I really need to thank them. In addition, I need to thank my advisor, and probably her favorite picture in the world, Dr. Nicole Benuso. These past 2 years have definitely been an adventure, but none of it would have been possible without your knowledge and guidance. In addition, Dr. Adam Woods, he not only sat on my committee, read my rather lengthy thesis, but helped tremendously with my nutrient analysis and showed me how to use the ICPS, among other things. And then, of course, Dr. Kirby for serving on my committee and then providing just support along the way. In addition, I really have to thank the EPE lab, Kelly and Bob, who could not be here today, but especially Mihai also. As Nicole said, they helped me sample, and if they weren't there that day, this project would have never have taken place. And as I said before, we have a lot of really interesting stories from that sampling experience, so I thank you for that. And Jasmine, who could not be here today, she went out with Nicole and I and helped us measure the strat section for the first time. And then finally, I just need to thank my friends and family for all their support and encouragement over the last 2 years. It's been a lot of fun. So I am done talking for right now. Does anyone have any questions?